All right, guys. So as we talk about the atomic structure, this arrangement of electrons around the nucleus of the atom, I figure the way we'd start this is by looking at experimental observable data. Okay. A lot of times when we address this, like maybe in your first year chemistry course, they did kind of the historical development, the Thomson experiment, the Rutherford experiment, and kind of how we build up to the model of the atom. I'm going to take a different approach. I'm going to do this in order to make this a little bit more concrete for you guys, so you guys can kind of see where all this comes from, see that it is based on experiment. We didn't make this stuff up. And so, it's kind of a result of the interpretation of this experimental data. And our central problem, once again, is why is it that we get these line spectra from these gaseous atomic emissions? So we excite the gas, and then we get the light, and instead of having a continuous rainbow of colors, a continuum, we have these lines. And why is that? This was the question that scientists were trying to address at the end of the 19th century, beginning of the 20th century. And it's one that we're going to look at as well. And so to start off with, let's think about kind of the physics of just what's happening between the electrons and the nucleus. So, in this physics, we have this positive nucleus. It's going to have some positive charge. And then around the nucleus, we're going to have, electrons, right? So if this was like the helium nucleus is +2, we'd have these electrons around it, right? And we know a few things. We know, first of all, that there's a force of attraction between these because they're opposite charges. Opposite charges attract. You guys learned this in grade school science, and the same is true in the atom. So this is what's holding those electrons around the nucleus. And so we know, because from this force of attraction, we know that the closer the charges are, where's that? Charges. The greater the force of attraction. Okay, the greater the force of attraction. Okay, so distance. Distance is important here. And electrons that are different distances from the nucleus will have different forces of attraction. And the other thing we know is that the greater the charge of the nucleus, the greater the force of attraction is going to be. Nucleus. The greater the force of attraction. Okay, so electrons will always have, what we call a -1 charge. So if the nucleus has a big positive charge, those electrons are going to feel more pulled in towards it than if it had a smaller positive charge. Okay, so we're going to start with those two facts. And there is a equation in physics that allows us to calculate this force of attraction between two charges, and this equation is called Coulomb's law. So what Coulomb's law says is that this force of attraction, in this case, is going to be the force of attraction. If these were like charges, it would be the force of repulsion. But this force of attraction is equal to some constant k. We're not going to worry about the value of that is. With some constant k, Q1 times Q2. Now, I apologize for this, guys. These don't mean heat. In this chapter, these are going to be charges. Okay, so these are charges. These are charges in this unit called coulombs. Okay, and to give you an idea of the size of a coulomb, one electron has a charge of -1.6 times 10 to the -19th coulombs. Okay, so that's the fundamental charge. When we say something has a -1 charge, what we mean is it had -1 times this number. It has -1.60 times 10 to the -19th coulombs. If it was a +2 charge, it would have a positive 2 times this charge. So charges are measured in coulombs, but we can see that this force of attraction is directly proportional to the product of these two charges. Okay, so the higher, the electron charge will always be the same. The higher the nuclear charge is, the greater this force of attraction is going to be. And then it's also proportional to the distance between the charges. Okay, so that's what this is. This is the distance between the charges. And it's equal to the square of that. So if I double the distance So if I double R, then what's going to happen is the force goes down by 4 times. Okay, so the force will decrease by 4 times. And that's because, you know, R doubles, so that's half of it, and then I square the R, and that's going to be 4 times. And so what do we see from Coulomb's law? And this is what Coulomb's law is, this equation, is that this force is, as we said, you know, it's directly proportional to the charges. The more charge, the more force of attraction. It's inversely proportional to the square of the distance. So the further away these charges are, the weaker the force of attraction is going to be. And in chemistry, you know, we like to deal with energies, right, instead of forces. And so we can kind of re-express Coulomb's law in terms of energy. V would be the potential energy. Okay, we call this the electrical potential energy, right?
And this is true. Okay, great. I'm just showing you guys.
Oh, sure. So in electric potential energy, we can express this electric potential energy, and it's going to look very similar. It's going to be Q1 times Q2 divided by R. Instead of R squared, it's going to be R. So if I double the distance between an electron and the nucleus, I've cut the energy, the potential energy of the system in half. But I want to explain a little bit about what we mean by this potential energy. So if I have a positive charge, okay, sitting right here, and then I have this little electron at some infinite distance away, so R is equal to infinity, I would say that the V for this whole system is 0 joules. Okay, it would have no potential energy. So I set my reference point. Potential is always relative to the reference point. I'm going to say that this has 0 joules. Now, as this electron moves in, what's going to happen is that the potential energy is going to go down. It's kind of like it's falling down a well or rolling down a hill. And then eventually, you know, as it gets closer, my potential energy becomes negative. Okay, so the closer this electron gets to the nucleus, the more potential energy it has. Now, here's the thing. As I said, it's kind of like falling down a well. So if 0 joules is up here, and this happens to be the potential energy of the electron, in order to separate the electron, in order to get the electron back to an infinity, I have to put in that much energy. I have to put energy into it to allow the electron to escape. Okay, and this energy is going to be called the ionization energy. Okay, it's going to be called the, so that's the energy I would need to put in to ionize, to form a positive ion for this atom. So for this ionization, as I said, we have this idea that we have this positive nucleus, okay, we have these electrons, and then somehow, okay, we put energy into it. And if the energy we put in is greater than or equal to the potential energy of the electron, then the electron separates from the atom, and the atom ionizes. Okay, now what we call the ionization energy is the energy, the minimum, let's say the minimum energy needed to remove an electron from an atom. Okay? And so what we're going to do in class is we're going to look at ionization energies. Okay, we're going to look at this at the ionization energies of atoms, and from that we're going to build up to a model that will allow us to explain those line spectra that we saw at the beginning of the presentation. So we'll talk more about this tomorrow. If you guys have any questions, please let me know.